Welcome back, everybody. I'm still Matt, and this is still the Hungry Microbiologist, and this is episode 2 of Getting Hungry, where we're going to work on designing some lab equipment for my Not a Lab. Today, we're working on a spectrometer. The reason why you're watching this in such terrible video quality is we're recording on my laptop camera, a downgrade from the cell phone camera I normally use to record, as I'm going to be running this spectrometer off of my cell phone's flashlight. Hadn't thought about the recording issues that would make when I designed it, and hopefully I find a workaround before we record the video this is being made for. So, spectrometers, what are they, and how do they work? The simple answer is they record the light initially and as it passes through a substance in solution. And by applying some equations to the difference of those, we are able to determine the concentration. Here's the more in-depth breakdown. It does involve very, very basic quantum physics. It's basic enough that I understood it, and hopefully that I can explain it. So, the electrons in any molecule exist at different energy levels. In nature, they are almost always at the ground state. However, they can increase in energy levels if we apply exactly enough energy. They cannot get energy and go to here. You have to apply enough energy for an electron to move from here to here, or to here. This is the root of quantum physics. Everything has to move in quantified amounts. So, how do we get that energy? Well, we use light. Light of a specific wavelength carries a specific energy. Once again, this is that whole wave-particle nonsense. What you need to know is a specific wavelength of light, the photons will have a specific energy. So, if this wavelength, lambda, is equal to the energy level that the electron needs to raise, we can move an electron from here to here, and as a result, we absorb the photon. With that photon not passing through, we now have absorbance, that decrease in the amount of light passing through the substance. With enough of these molecules absorbed in a solution, we can now calculate the concentration based on the number of photons of a known wavelength that were absorbed. So, what are we going to do for our spectrometer? Well, the first thing, as I mentioned, is we need a light source. In this case, that is my cell phone flashlight. It will be emitting wavelengths of all kinds of light. We'll deal with that later. Next, we need our sample. In this case, I have procured several scientific cuvettes. The cuvettes we use are 1 centimeter path length cuvettes. They're clear plastic. Plastic is not ideal for UV, but we are going to be working strictly within the color spectrum. So, a sample to hold there and absorb some of the light. Next, we need a filter. This will be a bandpass filter, only allowing a certain wavelength of light through. This will be the wavelength that we're studying. we place this at the end, not the beginning, because we want to limit the amount of stray light that can get through. Light can seep in from all kinds of outside sources, and by placing any filtration at the end, we actually reduce that effect. Stray light is the absolute bane of any spectroscopy experiment. So this is just one of those neat little tricks. It wouldn't matter if we place it at the beginning or the end, so we place it at the end just to help with that. That last little bit of light makes it through to a photoresistor, which we are reading the voltage across with, in my case, an Arduino computer, but whatever computational equipment you have. And that can either display the voltage, and then you can apply your own calculations for your blank or your initial light and your final light or your transmitted light. Or, in my case, you can program the computer to do it for you and display the result as an absorbance. That equation is as follows. You need the log of the initial light, or blank as I call it, over the transmitted light, and that provides you with your absorbance. As you can see, since we're dividing the light by the light, absorbance is a unitless value. That's important when we begin trying to apply absorbance to learn concentration. Absorbance equals path length times concentration times E. This is known as Beer's law. E is a constant that depends on your molecule and the wavelength that you're measuring. Therefore, its units must cancel out path length and concentration to give you absorbance. In this case, you can see here we have liters over centimeters times moles. It's nonsense, but it's what has to happen for it to be a constant to work. So, let's start working on designing our spectrometer. As we started to establish, I have a bit of a 3D printing fabrication workshop here. So let's go. Okay, so here we go. If we're going to keep using this as a 3D printer for more of these projects, I might have to invest in some kind of Octopi or whatever program we're using now to record those time lapses. But for the meantime, this is what we're going to have to do. Time lapse it like this. Look at this absolutely beautiful first layer, and holy fuck. Okay, so project's moving along. This is the main plate that will hold the phone, the cuvette, and eventually the electronic pieces will wire into it. Everything here is great with the tolerances. I got the cap to fit on tight, got the cover good. I like it. I like that it's firm and tight. We don't want any light leaking through, so I very specifically did that. However, one of my tolerances was a bit off. I have gotten multiple cuvettes stuck in this thing and had to shatter them to get them out. So we're reprinting the whole thing with a slightly bigger hole. Unfortunately, that's like a 8 to 9 hour print, so we'll be back later. Well, I tried to take the easy way out and simply make the hole in the center bigger. But now, the cuvette holder, the walls were too thin, and the whole thing came apart while I was trying to get out the supports. So it looks like I'm going to actually have to go back in for a proper redesign. And there we go. Printing is complete. Alright, welcome back. Assuming I remembered to record all of that footage the first time through, you have now seen my design process for working on this here spectrometer. There are a few changes because this is actually my second take. The first video had certain suboptimal developments. And if we're already going to be working with this poor video quality, I want to make sure we at least get a good quality video. So, here we also have all the electronics I was talking about. As with the last video, I will be posting a link to my code and to my circuit diagrams. But another factor that I'm quite proud of with this one is that I have designed this entirely using an Arduino kit that I was able to purchase. Almost like I'll be posting the actual name of it in the links, but it is baby's first Arduino. It has some prefab guides, not to making a spectrometer, but enough that I was able to figure it out, with this being only my second piece of Arduino-powered lab equipment. I'm starting to really love this stuff. So the way it works. First we'll take our blank. This is what we keep calling the incident light, or the initial light. We need our filter in place as well. With all the same conditions, but with none of the target molecule, we record how much of the light gets through. The way we do this is by closing this switch here. That is now a saved blank. Now we introduce a sample with a color. In this case, red. Since it is red, I am using a blue filter. Remember, we want to record the light that is absorbed by our sample. Something that transmits red light is absorbing somewhere on the opposite side of the spectrum. So, simple push of this button. We have an absorbance of 0.147. So what does that mean? On its own, it means very little. Like I said, what we need to do is use that E value. Now, there are times when you can simply look up an E value, times when you're measuring things like protein concentration or amino acid concentration, which end up really just being estimates anyway. With proteins, we biochemists like to measure the absorbance in an ultraviolet range, where it's actually just the aromatic amino acids that are absorbing, and we have a general guess that proteins will contain, on average, a certain number of aromatic amino acids. Or you can get more precise by calculating the number of aromatic amino acids in your protein of interest, but even then you're assuming you have a pure sample. So those are really estimates. If you need ultimate precision, you're going to have to make a calibration curve. Now, I do not have precise enough equipment to make a good calibration curve here. But what you want to do is take a mass of a sample, known as exactly as possible. Weigh it on a scale that can give you as many significant figures as possible. Dissolve that in an exactly known amount of stock. Once again, as many significant figures as possible. This calibrated glassware is both expensive and fragile, and I'll get into why we don't need it here in a second. There you want to make a series of dilutions using a graduated pipette, something that is designed to only take out exactly a certain amount of volume, say 1 or 5 milliliters. You put that into another graduated flask. So now you know that you have an exact ratio of solvent and sample. From there, you can calculate the exact mass of what you added, diluted, and rediluted using the simple equation 1 times V2 equals C1 times C2. Now that you know the exact concentration of each of these, you can plot them in a graph. Well, you can check their absorbance and plot the absorbance versus the concentration in a graph. My two theoretical points here, so of course I have a perfect R² value and a perfectly straight line. Using these absorbances, we apply our line equation, y equals mx plus b. We blanked with 0 concentration in our solvent. So 0 concentration should be what we set as 0 absorbance. B, therefore, the y-intercept is 0. Y equals slope times x. From there, we can then substitute in A equals slope times c. We know the equation. A equals c times path length times e. Path length was 1 centimeter, so we can eliminate it. A equals slope times c, and A equals e times c of this calibration curve is equal to e. Now, whenever we run an unknown concentration through our spectrometer, we can look at A equals path length, concentration, E. The spectrometer gives us A, path length is 1, we know E, we can determine C. Now, why am I not building or buying or working with all of our calibrated glassware for this next video? I went through a lot of trouble to build a spectrometer. Well, when we're going to check the OD600 of our media, we're not actually going to be looking at this fancy absorbance. If you followed through that and you don't think you can retain one more thing, it is perfectly fine to think of OD600 as the absorbance of our growing colonies of bacteria at 600 nanometers. That's fine, feel free to move on. What's really happening, though, is we're just looking at light that is physically blocked by the growing colonies. All that quantum physics and all that equations, those go out the window. The spectrometer is a convenient piece of instrumentation that allows us to look at the light passing through. We actually choose 600 nanometers because our media will absorb very little of it. The media, as you recall, is kind of a yellowy orangey color when I was looking at the solids. It's the same with the liquids. Most of the light will pass right through it, but some of it will interrupt on the bacteria itself, not be absorbed, simply cast a shadow, reduce the amount of light through, and allow us to get the OD600, as we call it, the optical density, not the absorbance. You can know that it's still in its log phase, that it's still increasing and growing. Once you have a solid experiment going, you may know that you want to induce or change cultures or do whatever you need to at a specific point of the growth stage, which you can correlate to a specific optical density. Anyway, I hope you liked this brief on spectrometers, and I hope you follow through to the next video to see how I apply it here in the Not a Lab to work with microbiology. And we will get back to drinking everything we find when I finally get some new media in. Meantime, all we have is this, so bottoms up, and I'll see you in the next one. For anyone interested in a deeper look at the instrumentation we have. And this whole thing here is just to hold it all together. The phone light source goes back here. I position it and then I clamp it in with these. I don't want it to move at all because it's all passing through a very small hole in this piece. That pinhole there, if we move side to side, we get more or less light passing through. So we don't want that. We want all these little thumb screws down tight to hold the phone in as tightly as possible. Then this piece here also just slips on. There's actually little recesses in place for it to slide into. This is again to prevent stray light. As I mentioned during the main video, the stray light is the absolute bane of all spectroscopy. Any light that's not coming from your incident source, not passing through your sample, can then cause trouble at your final end result. The electronics here are actually not that involved. The majority of what you see all these wires for is to run my LCD screen. Just so you have a better understanding. This is our Arduino component here. It is storing all of the power supplying and all of the equations. It's calculating the voltage through the resistor and then turning that into an absorbance for me. It's also saving our blank. I do that simply by working a switch over here, and by switch I mean I have a wire that I plug and unplug. Well, this orange wire is unplugged. It's listed as not ready. Once it's plugged in, the blank is saved. Then, when we put our sample in, since we're running through that nice constant power supply, the Arduino is stepping down this 9-volt battery to 5 volts. When we push this button, that's when it cues it to measure that resistance, and that's when it spits out our value. For this, it's just that 1 point value. So if you wanted to test 2 or 3 times and then average together, that could potentially be more accurate. You could also end up knocking some of the wires around since I keep this thing on a loose bit of breadboard and totally ruin the experiment. So, all up to your application. I hope that helps. Stay hungry.